All right, welcome to another coding session. Last time I was pretty happy that we managed to create this procedure, which is basically just a copy of this one up here. Same procedure, but this one has @glsl on it, which marks it as, well, a procedure that should be compiled to be used in GLSL. So it compiles it to a GLSL compute shader. And then we just have this ref because our compiler will ignore it if we never actually use it. So this is us using it so that it gets compiled. If we look in our assembly, we see that we get this here. So the code gets printed out as a variable in our data section. And then if we format it nicely, this is what we get. Something that looks a little bit, at least a little bit, like a shader, compute shader, but it's not quite there. So something that really stands out to me is that this index and data we don't actually have. Well, index we have here, so I guess it's data, but really this, after thinking about it for a little while, what I realized is that we don't really want this loop here at all, because this index needs to come from, it's like the, I don't know what you call it, I think it's called the invocation ID or something. Like essentially we want this program to run on a separate core for every index, for every element of the data array. We don't want to have a loop in each one. Having that loop makes sense when we're doing it on the CPU, because here when we take this task func and we boomstick it across this thread pool, we only have 8 threads here. So the reason that we only have 8 threads is because on the CPU, I think my CPU, if I open up my system thing, it'll say that we have 16 CPUs, but I think that's counting hyperthreading or whatever you call it, where they kind of claim that there's 2 CPUs per core, and I'm not convinced. So, I could do some more testing, but anyway, the idea is that I have a thread per core, because once you go above that, you can't just create a thread per task or something like that, because once you go above your core count, what happens is that you start having more overhead, because the cores now need to switch between threads to handle the amount of threads that you've created. The physical cores then need to switch between threads, and that has cost, that has overhead. So the optimal amount of threads to use and to fill with work is the same as the amount of cores, which is why we have 8, which what I'm trying to get to is the reason why task func here has a loop in it. Because, our data slice has a lot more than 8 elements. It has this many elements. So each core needs to process a whole bunch of them. But when we go to the GPU, we don't want to do that. Really, I'm going to put it on the left here. And eventually, we'll make it so that boomstick also has the same signature, but let's just start here like this, and then we'll just take away the loop. Right? So now we're just processing one element. Now, ideally, we wouldn't be initializing this in every invocation, but I think the cast is going to be pretty small, and our language can't really handle extracting this out at the moment, so we'll leave it in. But this is basically it. All we're doing is adding, this delta to a vector. Quite simple. We do it just once. So that's going to take this loop out. It's going to be just this basically. And then we need to think about, well, how do we get this index? And the way we do that is we need to, well, we haven't tried to invoke this yet, but essentially there is like an invocation ID. So maybe I have this other project that I used to work on. I haven't worked on it in ages, but I think I have the right files open. Where would it be? Compute shader. I think here we create a compute shader, quite a complex one. Here we go, global invocation ID. So I think I can just set it to this .x, and we'll explain that a bit later on. Maybe I'm doing this in a bit of a weird order here. But if we go to our GLSR generation for a program, it is going to mess with this a little bit, because what we really need to do is create our own braces and then have the first statement be int index equals this, right? And then the problem here is that this is going to be a scope. And actually we want it in here. Maybe I'll put a new line here just to separate it out a bit. So we want this here, but we can't, because this is a scope, it's going to print these brackets, which we don't want. So instead, actually, we want to get, well, maybe we have a look at the scope. Yeah, basically we want it without the braces. So we want to do this. I don't think this uses the index, so let's take that away. So that's more what we want, something like that. So I'm going to say, that's the right-hand side node. And this is the right-hand side node. I guess I'll call these right-hand side child nodes. So that should print out all the statements within the scope without the curly brackets, so that we can have this statement. So that should take care of that. If we run that and then have a look at this code, let's see what we get. Okay, need to replace the new lines. Okay, it would be nice if we have better indenting, but that's not really a priority right now. So we have this index, which we're getting from the global invocation ID. So, and we'll explain that later. Then we create a vec3. I think this equals 0 is not going to work, but we can figure that out later. And then we're adding our delta. Great, but we don't have data yet. So let's see if we can declare our data, which is a bit tricky because it's a slice. But let's have a go at it. So we'll get the left-hand side, I think is what we need. Yeah, because that's going to have the type info. And then in here, I guess we're going to, well, I guess it's for like all of the parameters. Param node in, well, I guess we need the procedure type node, which is the type of this. We need the children of that. Now, remember the index was the first parameter, so we're going to skip that. So we're going to start from the second parameter and then go onward. And we're going to print something out for each one. What was I thinking here? Okay, so if we go back to our other code here, this is another project I did which has a lot of OpenGL in it, so it's quite a handy place just to like steal some code that I can't remember how to do. Like this, if we're binding a OpenGL buffer, if we want to take data from an OpenGL buffer and make it available in the shader, this is how we do it. You know, we bind the buffer to a certain index, and then we say this is what's in it. So we're going to do something like that for each parameter, and then we're going to bind the parameters later on. And hopefully it'll make sense. So if I take this here like that, so this we will need the index, so we can use that in here. So I guess we've got index %i and make that a format line. And I'm going to call this the param whatever layout. I think you need to give each one of these a name. Like if we go back to this other code, you can see that like this is the grid layout, this is the command layout. I think they all have to have unique names. I can't remember exactly, but this should cover that. So we use index twice. And now we need to print out, well, I guess we need to print out this bracket. Just a print line. And there's a closing bracket with a semicolon. I guess actually this would go in there too, the empty line. So now this contents, it's always just going to be one element, which is the parameter data from the parameter node. So if and we're talking about a slice, which I'm going to take like this. I'm going to ignore the length and everything because, you know, a slice has a length and a pointer to the data, but this buffer that we're binding is this guy here, right, that we declared up here. So this is containing directly just this. I think the L, does that return a slice? Oh, it does too. That's kind of nice. It returns a slice, so it has a length and everything. But it's the raw data. That's what's actually in the VRAM. That's what's going to get bound to the shader. So it's not going to have the length. Maybe we can figure something out to handle that later on, but it's not the priority for today. So I guess this is going to have, I don't think these should have spaces actually. I think they're just like that. This one should have spaces because it's indented. So this here is because it's a slice, but this here is the type name. So we created that special type name. Oops. Procedure 4. Type name of this node. This is the name of the parameter. So that's just param node.value. And this here, just to be really simple, I'm just going to say, so let's get the type, let's extract that. Let's say if we're dealing with a slice, then we'll put the brackets. Otherwise, we'll just put nothing. We'll just keep it simple like that for now. We'll also need to deal with arrays, I guess, later on. Because we could, well, I guess, is it always going to be a slice? I don't know. Anyway, this will handle the immediate case, which is what we're worried about. So we'll put that. And then hopefully, if I run that, and we look at the code, it didn't crash, which is nice when I ran it to start with. We get nothing. It didn't print out anything. Because actually, we want the params type node. So the type node of a procedure has multiple children. Potentially the first child is the parameters, and that's what we want to look through. We could do some assert. I'm just going to put some asserts here for now. These kind of checks, I think, should actually go back to, instead of being asserts, they should be nice error messages, because these are things that are like, it passed type checking, but now when we generate, we discover, due to the limitations of the backend we're using, that we can't do certain things. Like, for instance, if we're generating a program here, then we need to make sure that this only has one child. Because if a procedure type node has two children, that means the second child is a return type, which we don't want. Must not return a value. Good enough. And then the other check I wanted to do was the length of parameters is greater than 0. And the first parameter, I guess it's 0. This is getting a bit complex to be just thrown straight into the assert, but hopefully it works. It needs to be an I32. You know, it needs to be the index. We have I32 or I64? We have I64 right now, but I'm going to change it to I32 because that's what's kind of native for these programs. So that should ensure that we have at least one parameter, and the first one is the index. I guess it needs to also have the name index, doesn't it? So that's even another check. So let's split these up. So this is must contain at least one param. So then I can do this. Extract that out safely, because I know, because I've just done this check, I know that this exists. So I can safely get that, and then I can say oh, this is the param 0 node, because I want to say param 0 node dot value equals index. and the type value equals I32. Okay, cool. So that's our checks. So let's see. Unsupported type name. Okay, that's probably coming from here. What did we handle here? Probably because it's a slice. So in our case, the type name of the slice will be what the slice is containing. That's what should go here, because the fact that it's a slice is kind of handled here. And I'll explain this a little bit more once we get it working. So I think I'm also gonna, because we're not ready to use this anymore, I think I'm just gonna like cut those out. So let's say this is just int, and I'm gonna say, yeah, procedure. I'm just gonna make all of these unsupported. Like so, and if it's a slice, we're just gonna get a type name, the child type name. So that should be the type name of what the slice contains, I believe. Let's see what happens. Okay, it compiled. Okay, this is looking pretty good. It's a slice of vec3s. So you can do this, have an array without a number in it. When you're declaring these bindings, these buffer bindings, it has to be the last element. You know, I couldn't put like float x here. This would have to be the last thing. So it's saying like there's some number of these things at the end of the buffer. So now we have this data vec3s. We still have this .raw, which is wrong now. We don't need to do that because we have the raw data here. So we're going to take away this .raw. And then I think the program is like basically done. Oh, we have to declare up here also. We have to have another declaration up there. But that's pretty much it. So what would it be? I think it's the identifier. We have a superfluous new line there, but that's fine. Maybe it's the primary. Here we go, .raw. So let's just cut that out. We don't need .raw. So that gets rid of the .raw. I also mentioned we need an extra declaration at the top. If we go to our other project, go to the top of this thing. We don't need that, but we do need this. So let's add that into our program. Let's put a new line there, and then this guy. I have to double check for performance things, but I think it's best if we just do 64 like that. So these are kind of geared up to be like three-dimensional invocation spaces, if that makes sense. That's why this invocation ID has XYZ on it. So you kind of get like a three-dimensional ID, but by saying that I have 64 on the x-axis and then just 1 on these, I'm kind of just reducing it to a 1D space, if that makes sense. And when we go to invoke it later, well, maybe not much later, because I think we've basically got it sorted now. You know, it should print out like this now. That should be the result we have, and I think that's should be a valid, fingers crossed, a valid, well, without .raw. shader, compute shader. Okay, so I guess the next step is to try compiling that. So what we can do, because this is effectively, this variable in here is basically a C string, right? It's the same format as these, you know, it's string data followed by comma 0. So it's null terminated. So it's basically a C string. So what I can do is just say C string untyped like that, and that should convert it to a C string. And then we should be able to compile it. So we have this code up here, compile shader. So we should be able to just pass this guy in here. We need to find the length of it. And we need to add this compute shader constant. So the length, I should be able to just go here. I kind of manually did this, but it should be right. So it is 299 characters. So put that there. And this compute shader will need to go in our standard library along with these guys. And I did look up, here's GL compute shader, should be this value. I like lowercase. We handle, when I first did these, we didn't handle hex, but now we do, so that should just work. So hopefully that should compile our shader and see what happens. Didn't look good. Well, the window came up, so yeah, it can't be in the compiler that the error is. It must have been in the code. Maybe we can search for this. Here we go. This immediately looks wrong. This is the assignment before this GL compute shader expression. So this is the GL compute shader expression, or the expression that uses it. This is the assignment before, and it's saying that both of these are on the stack. See, that's a stack address, that's a stack address. And it's copying from one to the other. But this is not on the stack. This is down here. So it's static. You know, it should be referred to the same as this is. Where is it? Here. So it should look like this. So the code that's responsible for that is when we generate an identifier. Yeah, it should be this stuff. So it's not a static procedure, and its allocator is not static, so it's going to the normal stuff. This is all stack-based stuff, so it needs to be handled by this. We could just do this, I think. I don't really like it, but I'm just going to put it to do, because eventually I want to have, you know, more backends, and we shouldn't have to hard code this stuff in here. There should be an easier way to tell that this is something that is essentially, we need to grab like this. You know, it's something that's embedded in the program like this. So later we need to do that better, but this should at least help. I don't know that it did help. It still doesn't seem to be referred to. If we find our compute shader, is it? Yeah, it's still showing like that. So the allocator is not coming through, maybe. Why would it not have the right allocator? Well, actually, something I'm kind of not really psyched about is that the allocator goes on the type. So when we have something like this, I really like the idea that this is the allocator. No, this is the type, this is the allocator, and they're two separate things. Like this is not part of this. It's like this and this both are parts of this, or like, you know, properties of this. Essentially is of this identifier. It's essentially what I would prefer it to be. So what I might try is just, I think I might need this later, but just put the allocator directly on the identifier. Let's have a look at where all the places that we do this. So instead of getting it from the type, we get it just directly from here. We sorted that out. So this is when we're parsing. So instead of adding it to the type node, we add it just to this node, the primary node. Parameters always need to be stack allocated, but we can just put it directly on the parameter node instead of getting the type. And this was when we resolve the types, we need to make sure the allocator goes through as well. But because we don't have the allocator on types anymore, it should not be a thing anymore. But the one thing that stands out still is when we come to like this, if we want this to keep the allocator from here, oh, maybe this is why it wasn't coming through, because we basically ignored the type of this and then just gave it a new type. And if the type of this is what was containing the allocator, then the allocator gets wiped out as well. Okay, so what we're doing should solve this. I was trying to explain something else, but I can't remember. Oh, so this is just an identifier, right? So when we go to resolve that identifier, when we're type checking, yeah, like exactly here. See, we're adding the type to it. Yeah, we're getting the type from the saved identifier and adding it to this node. Now that the allocator is a separate thing, we also need to add that. So this, I think there's two places where we do this here. Yeah, this is the same pattern. So that should make sure that it comes through, and this has the correct allocator. Okay, see, this is looking better, although it has the brackets around it, which the other C string that I showed, like this one, does not. The brackets are like the dereference operator. So, here it is. Let's close these other ones. Yeah, so it shouldn't, when we treat it as memory, that's why we get the square brackets. It should be just an immediate. So maybe really the logic here is that if it's got one of these allocators then it's a static thing embedded in the executable, in the assembly. And then we need to check, is it a pointer? Like procedures are essentially this is kind of the way that the assembly treats them. It treats procedures and also like C strings as pointers. But if it's just a number or something, then it treats it as an immediate. It's kind of weird. This is something that I don't really understand why it does that. Yeah, probably it's just a total misunderstanding from from my side. But I think we basically need to check, like, you know, is this a procedure? If it's a procedure or a C string, then we treat it as memory, right? Otherwise, it's immediate. I think that's the idea. So we need to get the type node from the node. So hopefully that will handle all of the static things correctly. It's not promising. No. Seems to be treating it as memory still. It's a C string, right? Okay. Yep, these are all integers, so they should be immediates. That makes sense to me. Wait a minute, did I say C string should be an immediate also? So is it just procedure that's treated like memory? I'm not sure about this. See now, so that looks right to me. But I think I've broken something else. That should be an immediate too. So maybe, where is this code? Maybe it was actually like this. Maybe I mixed them around. The procedure was an immediate. Okay, yeah. So procedures and C strings should be immediates. Everything else should be memory. Is that right? I mean, that seems more legit, actually. Expecting comma or semicolon line 14.1. Let's just grab the actual code and make sure we're looking at what was actually generated. But the fact that it's giving that error is promising. I'm really not confident, but I think that code I was just changing is right. This needs a semicolon on the end. And if we put a semicolon, it's like 200 characters now, 300. Exactly 300. And when we generate the program, we need semicolon there. Okay, uint cannot be assigned to variable of type int on line 12. This doesn't have line numbers. It's a very simple editor. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I guess this is a uint, should be a uint. Float cannot be assigned. Yeah, so that was, I remember this now. So we need to fix that. And once we remove that, that will be, so we added one character and we remove 1, 2, 3, 4. So essentially we are removing 3. Should be 297. And if we go to our generation of GLSL, and we're talking about an assignment now, it's this nullify stuff. So we need to handle non-integers. So we'll only do it for integers. Yeah, let's do that. So we need to do a linear search through type checking something, and what we're looking for is the just type node, and if it's assigned integer, then we do this. Otherwise we just don't put anything in right now, which is not really correct for our language, because one of the things about our language is that if you don't assign explicitly something when you're declaring a variable, it should be 0 initialized, and here we're not doing that for non-integers. So we do need to fix this up. That's a horrible import. Type checking dot assigned integer types. That's what I wanted. So hopefully that compiles now. Okay, so we get no errors. Perfect. I think we can get rid of that now. Okay. So we have a compiled compute shader. Actually, I think we do need to I always close things too quickly. I think we do need this compute stuff, because we need to create a program from it now. So I'm just going to do like a bunch of boilerplate code, essentially, to manually create an OpenGL program, and then down here we're going to manually run that program. But all of this kind of boilerplate is the kind of stuff that eventually we would like to remove, so that you should be able to just declare this and then do something similar to this boomstick call to run it later on. But just to get things working, we'll put a bunch of boilerplate. Got a shader name. Let's call that the program name. Don't need semicolons. We do now need gl dot, like so. So that's the shader name. So that should hopefully create a program. Let's just test that that runs. Okay, no errors, good. So that creates our program. Now down here we want to run it. And we also want to have something here which will, like we have this wait here. And when we run something on the GPU, I want something equivalent so that every frame we do our render, then we do our updating of the triangles, and then we wait for all that to finish before we continue with the next loop. And over here somewhere I had that, yeah, we need a fence. So I'm going to steal some of this code. And we're going to put a fence down before we render. Going to have to add a bunch of things. So create a fence. Honestly, I can't really remember how this stuff works, but I'm pretty sure if I go here to this grid tree and we scroll to the bottom somewhere, yeah, here it is. We do this in here also, where we just initialize a fence and then wait for it. So we'll just copy that code from init and wait, which also calls dinit. So this is the guts of it, basically. And timeout is, what is timeout? 1 second apparently, which is, I guess, is in nanoseconds or some very small number, very small increment. Okay, so hopefully that should, and then we're going to delete it, do this dinit, which is probably inefficient. Probably we only need to create one of these and then just use it each frame. But just to be very easy and not do anything different right now, let's just do this. So we're going to have to define these procedures, gl fence sync, all of these in here. So if I Google gl fence sync, has a gl enum and bit field, which I believe are both i32s effectively. And it needs to return the sync, right? Yeah, it returns a gl sync, which I think is also an i32. Or it's a 32-bit something, so I'm going to call it an i32. Gl client wait sync. What does that take? Let's Google that one. Returns a gl enum, so it also returns an i32. And this one's a 64. And Bitfield and gl sync i32. I mean, let's just double check this. There's somewhere there's like a field. What is it called? It's like, oh, not big field, bit field. This is what I was looking for. So this table has all the types and it has the bit depth, the size. So gl sync is pointer bits, the bit depth of CPU pointer addresses, which actually is 64. So where I had sync, go i64, that returns a sync. Flags is i32. This is clearly an i64. I mean, it's a uint in there, but doesn't matter. And it's returning, what was it returning? GL enum, that's a 32-bit. Okay. What was the other procedure? GL delete sync, which I assume just takes a sync. Let's see. Yeah, that's basically it. Okay, so those are declared. Now we need these two constants, GL sync GPU commands complete, which I also searched here. Where is it? This one. GL sync GPU commands complete. Yes. And GL sync flash commands bit, which is just 1. Okay, we're getting pretty close now. That should wait. Let's see if it's okay. No errors. It seems to have sped up a bit somehow. Wow. Probably because it wasn't waiting before, it was kind of like creating a massive backlog of work to do for the GPU. Something like that, maybe? I'm not sure, but it seems faster with the sync. That's nice. Okay, so this is basically saying GPU wait at this point. So now we want to run this program instead of doing this boomstick. So we comment that out, and we want to run the program. Let's steal some code from over here again. This is how we execute. Most of this is validation stuff, so let's just skip that for now. And we'll do something more like this, which is more essential to what we want to do. Okay, so we need GL dot. So that's going to be we're going to use this, which means that after we do this, when we go to render, we need to switch back to the render program, which is just called program name. Yeah, OpenGL is like a state machine, so you tell it which program to use, and it's like run that as a compute program. And now we tell it to use the render program, and then we do some rendering. There's another constant here. So this here, we need the name of the buffer. So we're going to have to do some bit of changes there. And this also is the 3D thing. So it gets a bit complicated, and to be honest, I don't understand it properly. But within the shade that we created, we said we want 64 on the x-axis. That's like per work group, I think they're called. And then out here, we're saying how many work groups do you want? So again, we just put 1 and 1, so it's like essentially reduces it to a one-dimensional thing. And here, it's like we want buffer data dot length. Where is it? Gone past it, haven't I? Buffer data dot length divided by 64. I think it is divisible by 64. Let's just double check. Yes, it is. Good. Yeah, so this is how many work groups we want, and each of them is going to handle 64 elements, which is why we divide the total amount by 64 to get the number of work groups. And this is also why in here the index is just where we are on the x-axis, because we're not using these other axes. So we can effectively just use this as a 1D index. Okay, and the reason for making this 64, don't quote me on this because I'm not a professional with this stuff, but the reason that the local size is 64 is because I believe AMD natively likes to use 64 and NVIDIA likes to use 32. So by saying 64, you make sure that you are capitalizing on both of them, because on NVIDIA it can just split it into two things behind the scenes, and this will use a whole thing of AMD. If we had a smaller number, it would not be as efficient on AMD. I don't really know how that stuff works, but apparently 64 is the magic number. That's all I know. Okay, so I think we have everything to run it. It's just this buffer name that we're missing. And unfortunately, our really nice, where is it? Our really nice VRAM allocator does not allow us to get the buffer name. If we go into our memory, here's our allocator. See, the buffer name is declared in here, but then it's just never saved or anything. So eventually, I guess we need something like a map to be maintained in the background, so that given a certain memory address, we can then map it to the buffer name and say, okay, this is what we want to use in our shader. But right now, as sad as I am to do it, I'm going to I'm going to comment that out. Since we're in here now and we have this, like this is a local procedure, which is why we couldn't use this when it was in the memory file, but we might as well check these. And then let's just say, I want to type it. Like this is just a pointer basically, so let's type it. We can say raw equals untyped that, and length equals that. Ah, no, this is an array. It's not a slice. So I think we can just do that. Okay. So now we should have the buffer data and the buffer name. And hopefully that works. Size is not defined. So we also need a buffer size, which is, I guess, the amount of elements times 3 times 4, because there's 3 elements in each vec3 and each of them is a 4-byte float. So that should be the size of the buffer. I32, I64. Ah, maybe this is supposed to be an I64. Bind buffer base is not. Okay, so we have a new procedure again. Bind buffer base. This is also new. So we have to add these in here. Bind buffer base. I guess it's similar to bind buffer. Let's have a look. Target index buffer. And they're all 32-bit. Okay, so it's just got an index in the middle. And dispatch compute. go here. And what does that need? These, which are all 32-bit. Our language doesn't have unsigned integers yet. It's taken so long for me to add unsigned integers, so that's why we're just using signed. Okay, and it doesn't return anything, does it? No. Okay, so that should be all the procedures. But we still need shader stuff. Shader storage buffer, which I think was I had also in here. This is the value. So maybe I should explain that a bit. This bit here is binding this buffer to index 0 of the shader storage buffers. And that correlates to this. See, it's binding it to index 0, and the buffers that appear in here are the shader storage buffers. So we're saying use this buffer, and then in the shader we're saying that buffer that we bound over here, this is what's in it. Okay, and then we say do the computation. Is it going to run now? Nope. Okay, 121. So length is 64. So I think we need an I32 here. Okay. We're getting invalid operation. Interesting. I wonder, this, I think we can just do that actually. And I might just double check. I don't know if I can't remember if we changed anything in here. I don't think we did, but I just want to make sure that we have the length right. 297, 297, okay. So if I take this out, we have no issues. So when I dispatch that compute, no. Is it just when I bind that? Is it this use program? Ah, shader name. That should be program name. That's what it is. Okay, those triangles don't look very healthy anymore. And the frame rate is terrible. Let's lift this out of the loop and just do it once. And maybe accentuate it a bit so we can see that the triangles are offset. Try that. Okay, so this is not just translating the triangles, it's mutilating them a little. And I'm pretty sure I know why this is. So in GLSL, the way that memory is packed, it's not always packed densely. So when you have a vec3 inside of a struct, or in this case inside of an array, the vec3s are actually memory aligned to 16 bytes. Now a vec3 is composed of 3 floats, which would normally be 12 bytes. But just the way that OpenGL will interpret this thing, this array, is that each vec3 is aligned to 16 bytes. So there's essentially a 4-byte gap in between each one. So I think the way to resolve this is that we change it to a vec4. Oh, just like I saw that just here. So that means the memory is going to be bigger. So the buffer size will be bigger. So we're going to make it a 4-element vector instead of a 3-element vector, which then essentially means that I can just change that so that the 4th element is 0 as well. It doesn't really matter what's in there, but we can do that. So then in memory it should be packed correctly. So let's make this vec4 with 4 elements. I'll just say everything's a vec4. Okay, now let's try. Oh, there was somewhere that I missed. Here we go. Failed to compile shader. Interesting. Okay. Yeah, I'm really curious how that broke the shader. So if I copied that, like vec4 should be a thing, right? So it's line 19, expected a semicolon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Huh. What's wrong with that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I don't really see what the problem is here. It's the same as it was before, just vec4s now. Oh, unexpected end of file. Always read your error messages, kids. Oh yeah, because we added this, so the file got bigger, and I've already forgotten what size it got to. Was it 309? 309. So we need to, this is horrible that we have to manually update this, but let's try it again. That does not seem to have solved our problem. Oh, there's one other place. Where do we do it? Up here. This here is saying, this is part of our rendering. It's saying that what we're passing into our rendering shader, which is this guy here, we're passing in a vec3 position. It's assuming they're tightly packed, but because we just added that gap between them, we need to tell it, where is it in this sea of code? So this is just saying it's tightly packed. Now I'm saying that they are 16 bytes. Each one takes up 16 bytes. So let's see if that works. Okay. Now we have some triangles and we can see, it's kind of hard to see, but you can sort of see that they are offset from the bottom left a bit. So if we reset that and then we take this code and put it back in here, you should see them move. Unexpected end of file. Did I? Oh, because I added the 2 zeros. Yeah, this is really shitty, but we'll fix it eventually. Okay, so that cruised. And look at that frame rate. Looking pretty good. Let's slow it down so we can actually see the thing move. Ah, another 2 characters. Okay, and we can see we're getting a higher frame rate. Like if we switch back to here, that's slower, got 800. And then if we switch back to our single threaded attempt, it's much slower. Okay, so that's pretty awesome. We managed to take this procedure, compile it to a GLSL compute shader, which we then compiled into a program and run every frame. I think that's enough for today. We're at 1:11, an hour 11 minutes. But we have a lot of boilerplate code. This, and particularly this is horrible. So I think maybe in the next episode or the next session, we can work towards getting rid of this boilerplate code, so we have something nicer to work with. Something more like this boomstick. I think that's a very nice goal to have. Yeah, and that's basically the goal of this language, right? That's basically solving the goal of this language. But then we need to just I want to spend a bit of time after that adding a few more other features to the language, just making it nicer to use, more well-rounded. And then I think we can move into completing some other projects using the language. Like show that it's actually useful, show that it actually works for a real problem. Yeah, but that's awesome. So we've gone from 200 frames or whatever it is to like, look at it, it's just, holy shit. Yeah, it's doing pretty fast. Actually sped up over time. Got up to over 6,000 FPS. And this single threaded CPU version was about 300. So it's like 20x. 20x, and all you have to do is write a simple function and eventually, hopefully, just do call boomstick. And then you get this kind of performance. That's pretty sweet. Okay, enough for today. Thanks for stopping by. Have a good one. Ciao for now.